It seems like the most obvious question in the world. If you want to go to the moon, why don't you just point your rocket at it and go, fly in a straight line, get there as fast as possible, come back home? Simple, right? Wrong. And the reason why reveals some of the most beautiful, elegant, and mind-bending physics in the entire universe. The truth is, you can't fly straight to the moon. Not because it's impossible, but because the universe doesn't work that way. And once you understand why, you'll never look at space the same way again. Hey Space Family, welcome back to D3, Discover Deep Dreams, your educational gateway to the cosmos and beyond. I'm your co-captain, and today we're diving into one of the most fundamental questions in spaceflight: orbital mechanics and why the path to the moon is anything but straight. This isn't just about getting from point A to point B, this is about understanding how gravity shapes everything in space, how energy works in orbital mechanics, and why the most efficient path to the moon is actually a beautifully curved dance through space guided by invisible gravitational forces. So buckle up, because space travel is way cooler than you think. Here's where most people get it wrong. They imagine space like a highway. You're on Earth. The moon is out there. You draw a line between them and follow it. But space isn't a highway. Space is a gravitational field. And everything in it, every object, every spacecraft, every atom, is constantly falling. When you launch a rocket from Earth, you're not starting from a stationary point. You're starting from a planet that's moving at approximately 67,000 miles per hour as it orbits the Sun. The moon is also moving. It's orbiting Earth at about 2,300 miles per hour, and both Earth and the moon are locked in a gravitational dance with the Sun, with each other, and with every other object in the solar system. If you tried to fly in a perfectly straight line from Earth to the moon, you'd immediately start fighting against gravity. Earth's gravity would be pulling you back. The moon's gravity would be pulling you forward, but not enough to overcome the gravitational influence of Earth at first. And the Sun's gravity, it's constantly tugging on everything. You would need massive, continuous engine burns to fight all these gravitational forces and maintain that straight line path. You'd be burning fuel constantly. You'd arrive at the moon with barely anything left in your tanks. And you'd have almost no fuel to slow down, go into orbit, or do anything useful once you got there. This is why nobody flies straight to the moon. It's energetically wasteful, it's impractical, and it completely ignores one of the most powerful tools available to space explorers, gravity itself. Here's where orbital mechanics becomes truly elegant. Instead of fighting gravity, spacecraft ride it. Every object in space has two types of energy: kinetic energy, the energy of motion, and potential energy, the energy stored by position in a gravitational field. The sum of these two energies is called orbital energy, and it determines the shape and size of an orbit. When you're on the surface of Earth, you have a specific amount of orbital energy. To escape Earth's gravity entirely and coast toward the moon, you need to add energy to your spacecraft. But here's the beautiful part. You don't need to add energy continuously. You add it during launch, through the rocket's engines, and then gravity takes over. Once you're in space, gravity isn't your enemy. Gravity is your guide. Think of it like rolling a ball down a hill and then up another hill. You add energy at the start by rolling it down the first hill. Gravity does the work on the way up the second hill, slowing the ball down as it climbs. The ball follows a curved path determined by gravity and the energy you gave it at the beginning. Spacecraft work the same way. You launch, burn your engines, and then you're in a curved trajectory determined by the gravitational forces acting on you and the energy you imparted at launch. The moon's gravity will eventually curve your path even more, and you'll swing around it in an arc. This is orbital mechanics, and it's not a limitation. It's the most efficient way to travel through space. Scientists and engineers have spent over a century figuring out the most fuel-efficient ways to move between orbits. One of the most important discoveries is something called the Hohmann transfer orbit. Imagine you're in orbit around Earth. You want to reach the moon. The Hohmann transfer is an elliptical orbit that touches your starting orbit at one point and your destination orbit at another point. It's named after Walter Hohmann, who figured this out back in 1925. Here's how it works. Your spacecraft is in a circular orbit around Earth. To reach the moon, you fire your engines once, just one burn, at a specific point in your orbit. This adds energy to your trajectory and stretches your orbit into an ellipse. The far point of that ellipse, called the apogee, reaches all the way to the moon's orbit. You coast along this elliptical path for about 4 days. You don't need engines burning the whole time. Gravity is doing the work. Your spacecraft is falling in a very specific way, an elliptical fall that takes you from Earth's orbit to the moon's orbit. When you arrive at the moon, you perform another engine burn, another burst of acceleration to adjust your trajectory for lunar flyby or lunar orbit insertion. 2 burns. That's it. And everything in between is gravity doing the heavy lifting. Compare this to trying to fly straight. You'd need constant engine burns to maintain your trajectory against gravity. You'd burn fuel the entire way. You'd arrive exhausted, literally and figuratively, with barely enough fuel to do anything useful. The Hohmann transfer uses the geometry of orbits and the laws of gravity to be incredibly fuel efficient. And that's why it's been the standard method for lunar missions since the Apollo era. Now let's take this concept even further. What if you could use gravity itself to speed up your spacecraft? This is where gravity assists, sometimes called gravity slingshots, come into play. And they're one of the most mind-bending applications of orbital mechanics. Here's the basic idea. If a spacecraft approaches a moving body, like the moon or another planet, on the right trajectory, the spacecraft can use that body's gravity to change direction and gain energy, all without burning a single drop of fuel. Imagine throwing a ball at a moving train. If you throw it at just the right angle, the ball bounces off and comes back toward you faster than it left your hand. The train's motion transferred energy to the ball. Spacecraft work the same way. When Artemis 2 approaches the moon on its free return trajectory, the moon's gravity will curve the spacecraft's path. The spacecraft will swing around the moon, and as it does, it will gain energy from the moon's gravitational field. It doesn't need to fire engines. Gravity does the work. This is why the free return trajectory is so brilliant. The spacecraft uses the moon's gravity to redirect itself back toward Earth without needing massive engine burns. It's like the moon is gently catching the spacecraft and throwing it back home. Spacecraft have used gravity assists with planets throughout the solar system. The Voyager probes used gravity assists from Jupiter and Saturn to reach escape velocity and leave the solar system entirely. NASA's Parker Solar Probe used gravity assists from Venus to slow down and dive closer to the Sun. Gravity assists are free energy if you know how to use them. Here's where orbital mechanics gets really complicated and really interesting. The Moon orbits Earth. Earth orbits the Sun. Spacecraft are caught in the gravitational influence of all 3 bodies simultaneously. The paths spacecraft take are determined by the gravitational pull of each body, the spacecraft's initial velocity, and the energy imparted by engine burns. This is called the 3-body problem, and it's one of the most complex problems in physics. There's no simple equation that tells you the exact trajectory. You have to use computers to calculate it, testing thousands of possible paths and finding the one that uses the least fuel while arriving at the right place at the right time. But here's the amazing part. Within this 3-body problem, there are special points in space called Lagrange points. These are places where the gravitational pull of 2 bodies, like Earth and Moon, balance each other out in such a way that an object can remain relatively stationary with respect to both bodies. NASA uses Lagrange points. The James Webb Space Telescope orbits at the Earth-Sun L2 Lagrange point about 1 million miles from Earth. Future lunar bases might use Lagrange points as staging areas for deep space missions. Lagrange points are like parking spots in space, places where gravity itself creates natural equilibrium. Understanding these points opens up entirely new possibilities for space exploration. Here's the fundamental truth. In a universe governed by gravity, straight lines don't really exist. Everything curves. Every path a spacecraft can take is curved by gravitational forces. When we talk about straight trajectories, we're really talking about the most direct curved path. The path that gravity naturally creates given the right initial conditions and energy. The most efficient path to the moon isn't a straight line, it's a beautifully curved ellipse that takes advantage of gravitational geometry. It's a path that was impossible to calculate before computers, but that makes perfect sense once you understand the physics. This is why orbital mechanics is so elegant. The universe isn't fighting you when you travel through space. If you understand the rules, if you understand gravity and orbital energy and the geometry of ellipses, the universe becomes your ally. Gravity does the work. You just have to know how to ask it. As we push deeper into space, into the moon, to Mars, to asteroids and beyond, trajectory design becomes even more sophisticated. We're discovering new Lagrange points. We're calculating gravity assists that chain multiple planetary flybys together. We're designing trajectories that use the solar wind, electromagnetic forces, and the gravity of distant moons. Future spacecraft might use trajectories we haven't even imagined yet, but they'll all be based on the same fundamental principle. Working with gravity, not against it, using the geometry of orbits and the laws of physics to accomplish incredible journeys with minimal fuel. The straight line to the moon was never possible, and that's not a limitation. It's an invitation to understand the universe at a deeper level. The next time you hear about a spacecraft heading to the moon or Mars, remember this. That curved path through space isn't a detour. It's the most efficient journey the laws of physics allow. It's gravity guiding the way. It's engineers and scientists working with the universe instead of against it. That's orbital mechanics. That's why we can't fly straight to the moon. And that's why space travel is one of humanity's greatest achievements. If you like space exploration, don't forget to like, subscribe, and share this video. Ring that notification bell so you never miss an episode of D3. Discover deep dreams, keep looking up.